One of the things that attracts many scientists to their profession is the excitement of discovering something new. You can imagine the excitement in the scientific community when the Large Hadron Collider recently found something entirely new. The discovered object is so elusive that some scientists have described it as a ghost. What has the collider just discovered? Why did it remain hidden for so long? In this video about the mysteries of the universe, we bring you how scientists just announced that the Large Hadron Collider has found something for the first time ever. Many people go about their day without knowing about the Large Hadron Collider. However, the discoveries made by the massive apparatus affect the life of everybody in the universe. Take as an example the latest particle that scientists just spotted for the first time with the help of the infrastructure. The Large Hadron Collider, or LHC, is the biggest and most powerful particle accelerator ever built. Covering an underground circular tunnel that is nearly 17 miles in circumference and costing billions of dollars, it is located at the European Particle Physics Laboratory (CERN) in Switzerland. But what exactly is a particle accelerator and why is it needed? It is a device that boosts subatomic particles to enormous energy in a controlled environment. This allows scientists to study the interaction that comes after. So basically, LHC helps scientists to test theoretical predictions and see if they have any loopholes. The LHC can be used to reproduce scenarios, including the conditions within a billionth of a second of the Big Bang. These include conditions that have never existed naturally since a few microseconds after the Big Bang. This facility is so key to modern scientific research that if there is any headline about subatomic particles, the LHC will most likely be involved. So when headlines across the world said physicists had detected ghost particles for the first time inside an atom smasher, it was obvious what equipment they used. Neutrinos are notoriously elusive, which is why news of the discovery made waves. The particle in question, the neutrino, opens up a completely new window for scientists carrying out subatomic research. They came a step closer to understanding the roles neutrinos play in the universe. While neutrinos are not easy to spot or catch, they are numerous in the universe. For instance, while you watch this video, about 100 billion neutrinos pass through each square centimeter of your body. But of course, you won't feel their entry or exit. These tiny particles are everywhere. They originate in nuclear fires produced by stars, supernova explosions, cosmic rays, radioactive decay, and more. Neutrinos manage to go undetected because they have zero electrical charges and nearly zero mass as well. They are 6 million times lighter than an electron. They almost don't react with any form of matter, but move at almost the speed of light. It is this elusive nature that makes people liken them to ghosts. But of course, if you try hard enough, you can catch neutrinos, but you must try very hard. A few experiments before now have discovered neutrinos. These include Japan's Super Kamiokande detector, Fermilab's Mini Boon, and the Antarctic Ice Cube detector. They all used a method known as the Cherenkov radiation, which is actually an indirect way to detect neutrinos. This is the gist of using the Cherenkov method to detect neutrinos. When a plane travels faster than the speed of sound, it creates a sonic boom. Similarly, when a particle travels at the speed of light through a light-slowing medium like water, it produces a faint blue glow that follows it. Scientists look for this glow when a neutrino strikes an atomic nucleus directly. However, this method only detects the signatures of neutrinos as they pass through the Earth coming from the Sun. It doesn't, for example, give any insight into the type of high-energy neutron that is produced when particles smash into each other, as can be observed in a particle accelerator like the LHC. On its own, the LHC cannot detect neutrinos. This is partly because the collider employs magnets to direct particles around a circular collision path with the detectors dotted around these curves. These magnetic traffic signs don't impact chargeless particles like neutrinos. As a result, they shoot off the edge of the detector path. To investigate this, scientists under the Phaser collaboration created a new neutrino detection mechanism, which they named the Phaser NU. This Phaser NU is made from dense metal plates of lead and tungsten. These plates sandwich some layers that can detect light, known as an emulsion. The first step is to make the neutrinos crash into the atomic nuclei on the metal plates, which produces particle byproducts. The next step is a familiar one for older photographers. The emulsion byproducts react with the neutrino byproducts, which imprints the outlines of the particles as they pass through the emulsion layers. When they developed the emulsion and analyzed the particle trails left behind, the researchers realized that some of the marks were produced by neutrinos. In fact, they were able to determine which of the three particle flavors of neutrino they had detected. The flavors are tau, muon, and electron. This result assured them that they had picked the right spot inside the gigantic LHC ring to detect neutrinos, and also that their new detector was actually able to see them. Phaser NU is better than the experiments before it in several ways. For instance, the Super Kamiokande requires 50,000 tons of water. In contrast, Phaser NU weighed only 29 kilograms. It was also made from leftover parts at CERN. Remember we said that there are three flavors of a neutrino. Tau neutrinos are the rarest and most challenging to detect. In fact, before the advent of Phaser NU, tau neutrinos had only been observed 10 times, the first time about 20 years ago. Phaser NU is powerful enough to detect different flavors of neutrinos, but it can also distinguish between neutrinos and antineutrinos. And here is where it gets interesting. Antineutrinos are just neutrinos with the opposite charge. You may recollect we said neutrinos do not possess a charge, and this information may appear contradictory. However, both neutrinos and antineutrinos are electromagnetically chargeless. The opposite charge actually stands for a neutron's lepton number, or a kind of quantum number used to describe the properties of subatomic particles. There are loads of questions that scientists don't have answers to just yet about neutrinos. For example, they do not know for certain the difference between a neutrino and an antineutrino. But Phaser NU will help them to learn more about neutrinos. The team behind Phaser NU said they would spend 2022 chasing and capturing 10,000 or more neutrinos. The answers to some of these questions will help in answering questions like where matter comes from and why so much of it is dark. Now, when scientists are investigating supernovas, you expect them to be observing the sky overhead, right? You'll be shocked to know where astronomers have been looking in recent times. The quest to know more about supernovas is making them examine trees for clues. They're examining tree rings for evidence of past supernovas. But what is the connection between trees on the Earth and supernovas occurring billions of miles away from us and billions of years ago? When a star dies, it often does so in a spectacular fashion. There is an explosion followed by the star's outer materials scattered in the universe. The result is that space gets bombarded with high-energy gamma radiation for several years. What scientists are trying to do is ferret out evidence of the death of stars from trees. Supernovas are not common, even though there are uncountable stars in the universe. While there is no way to determine how often a star explodes, even in our own Milky Way galaxy, some observations claim we could have between 1 to 3 supernovas in a century. But the most recent one in history took place more than 400 years ago. Robert Breckenridge is a geoscientist at the University of Colorado Boulder. He and his colleagues found what could be the fingerprints of nearby ancient supernovae in tree rings dating back to 40,000 years ago. The team claimed that in the last 15,000 years, there have been 4 supernovae close enough to Earth to leave their signature in the trees. So how does this work? The clue is the abundance of a radioactive isotope of carbon called carbon-14, or radiocarbon. Radiocarbon only occurs on Earth in trace amounts compared to the other naturally occurring carbon isotopes. Radiocarbon is formed in the upper atmosphere as it is bombarded by cosmic rays from space. When cosmic rays enter the atmosphere, they interact with the local nitrogen atoms to kick off a nuclear reaction that produces radiocarbon. And since cosmic rays are constantly streaming through space, Earth receives a more or less steady supply of radiocarbon. And if you know where to look, you will find radiocarbon. For example, some of this can be found naturally in tree rings, and every now and again, a large radiocarbon spike turns up in the tree rings, fading over several years. Since a rather significant known source of cosmic rays is solar activity, these spikes are usually interpreted as evidence of solar flares and storms. Every year, trees that are not near the equator grow during the temperate months but go dormant come winter. This pattern of growth and non-growth forms a ring inside the wood making up the tree. You can observe the ring when the tree is felled. The rings near the surface of the tree are the newest, and they age as the ring approaches the center. Counting the rings can reveal the age of a tree. A practical application is archaeologists using the pattern of tree rings in the wood found in ancient structures to determine when they were built. Breckenridge applied this knowledge to determine what might happen to tree rings when supernovae occur. He reasoned that a nearby supernova would give off vast amounts of what is called gamma radiation. Radiocarbon absorbed by a tree will make the rings more radioactive than one another. To test how valid the supernova hypothesis is, Breckenridge and his colleagues checked the record books. They compiled a list of known supernovae over the last 40,000 years. They were able to trace the supernova through the nebulous supernova remnants they left behind. Then they compared this list to the record of radiocarbon spikes in tree rings from the same period. What did they discover? Well, all 8 supernovas closest to the Earth seem to have matched periods of spikes in radiocarbon. For example, the Vela supernova, which exploded around 12,300 years ago at a distance of 800 light-years from Earth, corresponded with a 3% rise in radiocarbon. The G114.3 plus 00.3 supernova, which exploded around 7,700 years ago at a distance of around 2,300 light-years, corresponded with a 2% rise. There is also the Vela Junior, which was estimated to have occurred about 2,800 years ago. During that period, the Earth recorded a 1.4% radiocarbon spike. They also found supernova HB9, which took place some 5,400 years ago at a distance of between 1,000 and 4,000 light-years. This one corresponded with a 0.8% jump in radiocarbon levels. Scientists are now trying to validate Breckenridge's discovery. They are hoping that the tree rings method will help them nail the timing of many supernovas that have been difficult to date. They will also gain more understanding of how stars explode. Let's hear what you think of the mysteries of the universe in the comments section below.